Welcome to my talk entitled Hidden Amongst Chaos, Dynamics and Predictability of Weather on Subseasonal to Seasonal Timescales. Let's start with the motivation. Imagine a salesman approaching a farmer saying, "My seeds are only 5% more expensive, but they are super drought resistant." Before the farmer can judge if this is a worthwhile investment, he wonders if there is an increased risk for a hot and dry summer. So that evening, the farmer watches the weather forecast. But Gerrit shows the uncertainty plume. Well, predicting more than 10 days in advance is very difficult, and the models say it can either become very hot or very cold, leaving the farmer clueless. But we can actually do something. There are slow components in the climate system that possess predictive power beyond the typical weather prediction. They enable us to make predictions more than 2 weeks up to seasons in advance. But getting reliable predictions on these timescales remains a huge scientific challenge. In my PhD research, I have investigated the role of North Pacific Ocean temperatures for predicting weather in North America. So let's visualize these dynamics. On the left-hand side, you see ocean temperature deviations. And on the right-hand side, you see low-pressure systems in blue and high-pressure systems in red. If the ocean temperatures would lead to an increase in high-pressure systems over eastern North America, then we can also expect warmer and drier weather in that region. And this is precisely how the ocean can have predictive power for weather occurring thousands of kilometers away from the coastline. However, the challenge is that the ocean is evolving slowly, while the high and low pressure systems evolve fast and chaotically. And at first glance, there appears to be no relationship between these two systems. To investigate long-range predictability, the traditional approach is to use dynamical models that simulate the ocean and atmospheric dynamics. However, dynamical models struggle with the small scale and fast processes. But precisely these are important for getting long-range weather predictability. So perhaps the power of machine learning can help. Machine learning can efficiently search for a relationship by scanning through many observations. Subsequently, this model can use the ocean state to predict land surface temperature at a specific time horizon. But can we use this technique to actually predict heat waves far in advance? The quality of these predictions can be tested by computing how well the model is able to predict past observations. And we can compute different metrics for this. For example, the metric AUC confirms that there is a relationship between our probabilistic forecast and the heat wave occurrences. However, a relationship does not necessarily mean that we can trust the probabilities that we forecast. And the metric rare scale score conveys that we can actually not trust these probabilities. So different metrics communicate a different story, and it is important that we understand these statistical concepts. So we are faced with a trade-off. In an ideal world, a user would like to be informed about the very extremes with high spatial detail and know the exact timing of the extreme. In reality, we need to simplify the prediction task due to the chaotic nature of weather. We can only predict moderate events with low spatial detail, and we cannot predict the exact timing of the heat wave. To improve the reliability of the heat wave forecast, I needed to simplify the prediction task, and I also implemented improvements to the machine learning design. This enabled us to predict moderate heat waves up to 60 days in advance. However, being able to predict something does not necessarily mean causation. So I wanted to know if the ocean is actually influencing the atmosphere or perhaps vice versa. Basically, I wanted to disentangle cause and effect. And for this, I used a causal discovery algorithm. And the algorithm uses logic and statistical tests to discover causality purely from data. If we then study the evolution of ocean-atmosphere interaction throughout the year, an interesting picture emerges. In winter, the atmosphere is influencing the ocean, leaving an imprint in the ocean temperatures. In spring, we observe a two-way positive feedback, while in summer, the ocean is influencing the atmosphere and thereby affecting the occurrence of high-pressure systems over Eastern North America. Now that we understand these physics better, we can redesign and improve our forecasting method. And these results also suggest that the winter dynamics might provide us with valuable information for the upcoming summer weather. So let's get back to the problem of the farmer. We want to make predictions prior to sowing, such that the farmer can make an informed decision on whether to buy the more expensive but drought-resistant seeds. However, the current state-of-the-art prediction is released only in August. We use machine learning in combination with a causal selection tool to improve the trustworthiness of our forecast. And using this forecast, we were able to predict poor harvest years already in February with a precision of 66%, which is a doubling in probability compared to having no information at all. It is important to note that this performance is achieved on average, because forecasts are more reliable when the ocean temperatures are in a more extreme state. During such extreme states, the precision increases up to 75%. With the rise of extreme weather and the ongoing energy transition, weather predictions become more and more important. It is my vision to help the scientific community, as well as to bring these innovations to society. I have talked about the importance of getting the statistics right, but this takes time and effort. With the AI for S2S project, we are developing software that helps and guides the user to implement the proper statistics. It is important to have a good understanding of the physics, as this helps to improve the model design as well as trustworthiness. And finally, to have a meaningful impact, we need to be fully aware of what the user precisely needs. Bringing all these aspects together and being backed by an amazing team, we are starting the spin-off company Beyond Weather. And we hope to become a vehicle for scientific valorization within the domain of long-range weather forecasting. So with the company, we are operationalizing forecasts for the energy as well as agricultural sector, and we plan to help humanitarian organizations against non-profit tariffs. So this work suggests that we were underestimating the true predictability of weather on subseasonal to seasonal timescales. It simply was hidden amongst chaos.
Thank you. I invite the supervisors and the committee members to take their place behind the table.